All right, so let's talk about permutation and elimination matrices. So I claim we had two examples kind of already. Let me forget that for a second and just start with an example. So the example I want to start with is the matrix 1, 0, minus 2, 1. And I would like to multiply this by the matrix 1, 3, 2, 4. Pretty good with this? So ultimately, the kind of thought I'm having here is that I'd like to be able to do elimination without, well, frankly, without writing down x's, y's, and z's all the damn time. So I noticed some weird behavior before, and I just want to check that it works the way I think it does. So if you do this multiplication, I'm going to make this a little bigger. First, how many entries do I expect to have in here in my result?
Two.
By
2.
there we go. So the reason I expect that matrix to be 2 by 2 is that these two matrices were 2 by 2. And these two middle numbers match, which means that I can do this multiplication, and then the outside numbers tell me the dimension of this thing. Pretty good with that? Okay. Now, what is this first entry right here? How do you figure that out? I'm going to pick up the vector 1, 2, and do what with it?
Turn it sideways and drop it onto 1, 0, negative 2, 1.
Yep, so I'm going to pick it up, I'm going to twist it sideways, and I'm going to drop it onto that top row, calculating a dot product. So this first item here is going to be 1 times 1 plus 0 times 2. So that's the first row here, dotted with the first column there. Then my next spot that I usually go is this entry, which is going to be negative 2 times 1 plus 1 times 2. That's this first column dotted with this second row. Pretty good with that? Okay, then I'm going to take 3, 4 and dot it with this guy. So I'm going to get 3 out of that. Then I'm going to take 3, 4 and dot it with this guy. And I'm going to get negative 2 out of that, I think. You guys with me on that? Oh, actually, let me write that out to be immensely clear. Okay, so this is going to be 3. Oops, I'm writing this the other order. So this is going to be 1 times 3 plus 0 times 4. And this guy is going to be negative 2 times 2 plus 1 times 4. You guys all on board with this? Okay, so this top row is 1 and then 3. You guys all see that? So I might notice that that's 1 times the first row plus 0 times the second row. So this is 1 times the vector 1, 3 plus 0 times the vector 2, 4. You guys with me on that? Okay, what's the second row?
0, 0.
It should be 0, negative 2.
Oh, I'm a goofball. Sorry. That was supposed to be a 3. So 0, negative 2. And that is 1 times the first row. Oops, is it 1 times the first row? What got multiplied by the first row there? That'd be this
3.
component and that one. That was -2 times the first row plus the second row. So the action of this matrix is the new row 1 is the old row 1. And the new row 2 is the old row 2 minus twice row 1. You guys see that? Okay, now this feels a little bit weird, right? Like, why the hell do I give a hoot? So remember that sometimes we're going to be trying to solve equations, right? So the other day, one of my equations was that I wanted to solve was x plus 3y is 9 and 2x plus 4y is 14. You guys with me on that?
No, where's the 9 and the 14? Where'd that come from?
Oh, it's one of my examples from the other day.
Good.
It is from this conversation that was a video. Video is called The Idea of Elimination on the YouTube channel. Okay, so for whatever reason, suppose I had this thing, right? And I want to solve this with elimination. So one way I can do that is by like, oh, okay, so I can look at this first row and I can think, okay, so if I multiply that first row by -2 and add it to the second row, then I'll get an equation that doesn't have any x's in it. And then I could back substitute, right? Dealing with the x's and the y's is kind of annoying, which is really kind of the primary reason for doing this. So my first thing I'm going to do is I'm just going to take that thing and I'm going to turn it into a matrix system. So we're going to kind of think linear algebra at this. So if I think linear algebra at this thing, I get this matrix 1, 3, 2, 4 times this vector x, y. And that's going to equal this vector 9, 14. You guys see that? And then I noticed that, hey, if you take this thing and you multiply it by this elimination matrix that I just came up with, then I can get a 0 in there. And that's going to get me closer to being done with this problem. You guys see this? So I'm going to think to myself, all right, look, if I take this whole equation and I'm going to multiply that whole equation by 1, 0, -2, 1. Then I'm going to get, well, I already figured out what I get here. I get 1, 3, 0, -2. That's still multiplied by xy. And now on the other side, that's going to equal, oops, that got a little small. On the other side, that's going to equal 1, 0, -2, 1 times 9, 14. You guys see this? Okay, now the right-hand side I can calculate a little bit more, right? That's going to be 9 and then -4. You guys with me on this? Okay, so let me think about another step I could do. I'm going to kind of over manipulate this. Like I know that we're done. You guys all see that we're done here. Like at this stage, what do I know about y?
Y equals to 2.
Yeah, I know y is 2 because negative 2y is negative 4, so y has to be 2. And then I could figure out what x is by plugging 2 back in up here or something. Does everybody follow that the next steps I'm doing are kind of overkill? So I'd like to make my life a little easier. I'd like to target this negative 2. So what matrix can I multiply on the left to get that negative 2 to become a 1? What do you want to do to that second row? What do you want to multiply that second row by to get negative 2 to become a 1?
Negative 1/2.
Perfect. Right, and notice that's the exact same algebra step that you would have done to solve, right? Just divide by negative 2. So I'm going to put that in for the kind of row place, right? I'm going to put zeros in there. What do I want row 1 to do? I don't know. For right now, I'm just going to let row 1 chill. Does that make sense? So if I do this multiplication, I might kind of walk off in the margin, right? So I want to take this matrix and multiply by this one. Okay, so if I pick this up and drop it on, I'm going to get 1. If I pick this up and drop it on, I'm going to get a 3. Oops, sorry, I just did that the other way than I taught you. So if I pick this up and drop it on the bottom, I'm going to get 0. And if I pick this guy up and drop it on the bottom, I'm going to get 1. And then on my, I need to take this vector and multiply by that matrix. So that's going to be 1, 0, 0 minus 1/2. And then I need to multiply this by 9, negative 4. And out of that, I'm going to get the vector 9 and the vector, or sorry, the number 9 and the number, what, for the bottom? 2. Guys with me? That would tell you y is 2. Guys following along with this? Okay, so these are elimination matrices, right? Well, this one's not strictly an elimination matrix. I don't really have a good name for this. This is like a scalar kind of multiply. You guys see that? But this other one's an elimination matrix. So in order to do that process of elimination, you can just think of it as repeated products with these elimination matrices. And this, like writing everything as an equation gets a little tedious, right? You guys see I'm getting kind of like, frankly, a little bit annoyed that I have this equal sign and this XY in the middle. I thought the point was to save ink. So if you want to save even more ink, you can do what's called an augmented matrix. Have you guys seen augmented matrices before? They're sometimes covered in like algebra. They don't tell you why it works, but here's the gist of it. Put your matrix on the kind of left-hand side, and then instead of putting another one of these guys, put a vertical bar, and then put the vector that belongs on the other side of the equation. And then you can treat this whole thing as a single 2x3 matrix and do the multiplications with it. You just keep that bar in there. So if we multiplied this thing by 1, 0, negative 2, 1, I guess I really should make that arrow. I'm going to make that arrow point that way because I want it to be obvious that I'm doing that on the left. So if I do that, I'm going to get 1, 3, 0, negative 2, and augmented by 9, negative 4. That'll be this exact same thing because you're really just applying this matrix to the columns, right? Which is exactly how we got this vector anyways. Does that sort of follow? Now, the good news is that there's a button on your calculator to do most of this. So ultimately here at the bottom, I would get to the augmented matrix 1, 3, 0, 1, augmented by 9, 2. You guys with me on that? If you want to do this on a TI calculator, or if you want to Google something on the internet to get from here to there, that is reduced echelon form. If you want to go even further and get the identity matrix on the left-hand side so you can just read off what X and Y are, there's a... oh, sorry, I said reduced. This is not reduced. My bad, I misspoke. That is row echelon form. The further step that you can get to is reduced row echelon form. And in this case, that would be 1, 0 augmented by 3 and 0, 1 augmented by 2. Does that make sense? Probably not. When you guys all have your mics off, I can't tell whether I'm making sense and you're bored or whether I've lost you hours ago.
It made sense.
Thank you, Cody. Okay, so let me know when you get confused as hell, because this is kind of confusing. The permutation matrices are roughly the ones that we talked about when we were talking about matrix multiplication. They look kind of like this. They're a little bit like a Sudoku puzzle, except with lots of zeros in them. Each column adds to 1, each row adds to 1, and the entries are either 0 or 1. And what they do is they flip around the rows. Those do get a little bit complicated, but you guys got this. It is not as hard as it seems. It just seems really hard because there's lots of notation today. Okay, that's what I got for the day. Any questions on this?